Right, we start projectile motion. And before we start with projectile motion, we need to define a few terms. So the first one is, what is a projectile? A projectile is any object that's thrown, launched, projected into the air, and it has no internal energy source. A rocket is not a projectile. A rocket has engines. The space shuttle has engines. However, a bullet, a ball, are all projectiles, which means once they are thrown out of the gun or out of your hand, they no longer are able to switch on their engines and keep on flying. A plane is not a projectile, because if it turned its engines off, what would happen to it? It would plummet to everyone's doom. Sorry, doom. Okay. Trajectory. Trajectory is simply the path of the projectile that follows through flight. Right here. We all got that down? Now, to understand what projectile motion and how it's developed over time, we have to understand firstly what it was like back in the 1200s, during the Dark Ages. Okay? When we first learned how to project something. We've been projecting things for a very long time. Mostly the first thing that we projected as a species, as humans, would have been a rock. We would have thrown it. Then it would have been spears, then arrows, and then finally in the 1800s onward, we will start using cannons and then guns, and basically it ended there. And artillery is what happened. Now, the diagram you see here is taken from, it's a modern version, rendition of the artillery guide to the British Armoury back before Galileo. And this is what they thought. To bomb something, you popped it into your cannon, or in these days it was a trebuchet, which is one of those, it's like a big slingshot that you see on the Hobbit or something like that. You've seen those things. They don't have gunpowder. If they did, it's sort of useless. Okay? And once it's gone out, it used to basically go under a near straight path. And then what the cannon would give it, or the trebuchet, the launch, the slingshot, would give the cannonball, or whatever is projected, impetus. And the impetus was the word that they used. Impetus is just a Latin word for force, okay? Or, well, what we now use the word impulse for. That's where we get the word impulse from. And you get this linear violent motion coming out, up to the top, and as it came out, it would start magically. Remember, this is the years of magic, of alchemy, where you can, you don't know what's going on, whether the demons are taking it away or whatever. We magically lose impetus to the environment. And as soon as the cannonball loses all its impetus that it gained from the cannon, it would simply plummet straight down to the ground. So the path that a cannonball takes is this, up and then basically a natural drop. So if you were trying to bomb something, then this is not a very successful diagram. And most people who did bomb things, or bombardiers and whatever, they totally ignored this. They knew what they were doing. Okay, you just fired it. If it didn't hit, you were over it, you'd lower it, have another go. If not, you raised your cannon and kept on going until basically, yeah, I got it. Okay. Now, a fellow by the name of Galileo thought this was total rubbish. And he did a lot of experiments to try and work out how projectile motion, or what he called the motion of the parabola, was developed, okay, or how it could be described. So this idea that we have of the impetus has lasted from the first time it's recorded in history is in Aristotle's works. Okay, Aristotle. Aristotle's around about 800, 600 BC. Now, he would have been the person who comes up with it. He would have already been taught that himself. So we are talking the ancient Greeks all the way up until Galileo in the 1400s. Okay? This is what they thought the motion of a projected particle did. Okay? And everyone accepted it, even though we never saw this. Okay? It's obvious if I throw this water bottle and I project it this way, that it goes into this path. It doesn't go up and then straight down. But it's part of modern culture. It is part of our psyche. It has been here for so long that we even still today have remnants of it. Now hopefully this will work. Okay. Did we see the loss of impetus there?
Yes.
Right. It's still in our, especially in the Wile E. Coyote and Roadrunner part. You know that Wile E. Coyote used to run off the cliff and always hold up a sign saying, and he used to blink, going blink, blink, you know, and then help, then straight down. It's part of popular culture. We've taught kids for so long that if you run off a cliff, you run off straight until you lose your impetus and then you will drop straight down. You have been brainwashed into thinking that. That is the old Aristotelian, Aristotle's view of loss of impetus. Okay? Galileo didn't. Galileo did experiments. He was a scientist. Aristotle was a very great philosopher, but he wasn't a scientist. And he tried to collect all the common knowledge of the time and put it in his books. Galileo didn't do that. He decided that he needed evidence. He was a scientist. So he did all the experiments. He rolled cannonballs down sandy pathways and trekked their tracks as they went down the sand, and he found that they made curves. He measured these curves and found that they were parabolas. And he was a very good mathematician. He could calculate the formula of the mathematical pathway and so on. After a while, he comes to this conclusion that a projectile motion is composed not of one motion, but two motions. A constant sideways motion and a varying vertical motion. Okay? So the two motions are, if I was to project this water bottle at this angle up here, like that, okay, what it really is doing is it's just travelling sideways. At the same time, it's travelling up and down. Okay? When those two motions are combined together, you get the traditional parabolic motion. But in reality, all the water bottle is doing is going up and down, vertical motion under gravity, and because it's going up and down, its motion, in other words, it starts to slow and comes to a halt at the top and come back down, is varying. But at the same time, there is a sideways motion which has no force acting on it, and you're just moving sideways. The combination of these two mathematically gives you a parabolic path. I'll be okay with Galileo's view. Now, you are asked in question 2 there to describe Galileo's contribution to parabolic motion or projectile motion. The way that you would answer that would be that you need to mention the Aristotelian view beforehand. You would need to then come up with, you're going to do a little bit of research tonight about how Galileo actually did this. It's in your textbook. And then come up with the idea of his conclusions, which is that there are two motions, not one, in a projection. Are you okay with that? Now that's what that little box on the side there says. Over the next few days, you'll also have to fill in question 3 there, which is the little box saying complete the following table, which compares the two motions. And as we go through, you can add more and more to this stuff, into these 2 boxes. Are we okay with that? Rightio. On the screen at the moment, you have just some calculation using G as 10, that's minus 10 down. What would happen for 10 seconds if I just simply threw a ball upward? It starts at 0 and... No, sorry, it starts at 0 up here, and I'm throwing it up at 100 metres per second. Eventually, at the top of the flight, it goes down to 0 metres per second. Do we expect that to happen? What's causing it to get slower and slower? Right, it's gravity. The acceleration of the force of gravity is pulling the balls down, and that accelerates it towards the centre. Even though it's moving away, it's been accelerated downward. Okay? So if I was to put these plots over here, so we start at 0, and then the next, at time equaling 2 seconds, we're at 90. At time equaling 0, we're 0, then it's 95, that's there. Then the next is 180. These things never work. No, wait. 180, then 255, then 320, then 420, then 455, then 480, then there's another 2 over top of each other, and then 500. Okay? So that's the projection of the ball going vertically. Okay? If I also was to throw this ball sideways at a small speed, and this is also where it is at time equaling 1 second, we're at time equaling 10, and then at 2 seconds we're at 20, and then 3 at 30, and then 4, and so on. I keep on doing that. So at the moment they're 2 different balls. Okay. What can you tell me about the blue ball's motion? Is it constant or is it varying? Constant. What gives you the idea it's a constant motion? Right. The gaps between them are equal. Right. But this is not 2 different balls. It's not a red ball being thrown up and a blue ball being thrown sideways. This is the same ball. So where is it at each time? We have to combine the motions, and I'll do it in that pink colour. At time equaling 0 would be here. At time equal there, we just combine the 2 motions, would be there. At time equaling this one, will be there. And there would be there. And there would be there. Okay, you got my point, I'll just quickly do it. my last docs, I think, okay, it's not very good, okay? I think I misread those values up there. Okay, but what shape is made when we combine those all? Parabola, good. And we get a constant horizontal velocity, but a varying vertical velocity. The varying vertical velocity we practiced yesterday. Okay? And all you have to do is apply the same rules as we have been. The constant horizontal velocity we did in the beginning of the preliminary year. Okay, and there's nothing really strange about that. Okay. So, on your blue books, question 4 there says on the black ball that you have to draw all the forces that travels along. Okay, so the ball is at this point just there. Okay? Now, no matter where it is on the path, here it's been pulled down by the force of gravity. What's the technical name for force of gravity? Weight. At that point there, has the mass of the ball changed? Has G changed? So has the weight force changed? No. So the weight force is still pulling it down. It doesn't matter where it is, the force of gravity is pulling it directly down. That's what's causing the variable velocity to go down. So on our little blue or black ball for you there, it's only got that force pulling it down. What's the cause of that force again? The gravitational field of the Earth. So it's caused by the mass of the Earth. Okay? Remember, I've thrown this ball now out of my hands sideways. Are there magical pushing fairies still pushing it sideways?
Yes.
Did you see those pushing fairies? Watch again. You can see them if you squint your eyes. There's none, is there? Okay, they don't exist. Magical pushing fairies don't exist. So, are there forces pushing the ball further, faster sideways? No. Are there any magical pushing evil pushing fairies, because they'll be pushing backward? Would they be pushing it and slowing it down?
Yeah.
No. There is. You are going to say there's evil air-resistant fairies, aren't they? Yeah. We're going to ignore air resistance, okay? We have to do this, otherwise it becomes 4-unit mathematics. Okay. So, there's no forces sideways. There are no horizontal forces. If there are no horizontal forces pushing you sideways, will you accelerate sideways? Will you get slower sideways? Will you get faster sideways? The answer to all those questions is no. That's the reason why you simply move sideways at a constant velocity. However, are there forces pulling you down vertically? Yes. That's the reason why the vertical motion is changeable. Okay? There are no forces in the horizontal direction. So if you're going back to that box that you are filling in for question 3 there, what is a key difference between the two motions, the horizontal and the vertical motion? One of the key differences is that there is only a force on the vertical motion pulling it down. There are no forces on the horizontal motion speeding it up sideways. This means a key difference is that the vertical motion is changeable as the horizontal motion is constant. Okay? But now, this blue arrow does not represent a force. It just represents the velocity, the sideways velocity. When you first throw the ball as a projection, it starts moving sideways. How do I know it's moving sideways? Well, right, we see it moving sideways. That's the best evidence. It's eyewitness testimony. Now, that there means that it's moving sideways. At the top of the path there, is it still moving sideways? Yes, it is. Is it moving sideways in all parts of the path?
Yes.
Yes. It does not matter where you are, it is still moving sideways. That's a very key difference. That there is always horizontal or sideways motion of the projectile. Why is it a key difference to the vertical? Because at the top of the path, is there any vertical velocity? No. Remember, it's just two motions. It's been thrown up and down here, and it's been thrown that way at the same time. This is my vertical velocity, ladies, and this is the horizontal, ladies. Okay. So, at the top of the path, when just threw that ball up, what happened at the top of the path? It no longer rises. Vertical velocity, Vy equals 0. So at the top of this path there, Vy equals 0. But does horizontal motion still exist? Yes. Are we clear on that? You have to see these two motions as totally separate, even though they are combining for a single shape. While we're here, you'll learn that there are different types or classifications of a projection. The range is always a distance between the point of projection and when it strikes the ground. Okay? So range is always the horizontal distance along the x-axis. Right, getting back to my vertical velocities again. When you first throw this ball or project it, and we're just looking at the vertical velocity upward is huge. No. Is huge. So firstly, the ball has a large vertical velocity. It starts losing vertical velocity. Why? What force is causing? Right, the wave force, the force of gravity. And it keeps on losing vertical velocity as it goes further and further around until at the top of the path it has no vertical velocity. Then it starts to fall. And these arrows that we are seeing here in blue are simply found by the equations of the motions that we used yesterday. And as it comes down, what do you notice about the motion? It is symmetrical. What goes up comes down in the exact opposite method. So finally and lastly, okay, so those big blue arrows represent the vertical velocity. This original blue arrow just here must represent the original vertical initial velocity. Must it? Okay? So how do I work out the initial vertical velocity? Well, we do it by this triangle. I want you to imagine that we're projecting an object at this angle. Now, we've all seen volleyballers do it. You know how to serve in volleyball. You put your fist at the right angle, you hold the ball, and then you have to hit the ball at the right angle. And that's my computer. Right here. It's not a volleyball. Okay, that means that I'm projecting it at this angle here. Okay? And that angle there is theta. Okay? And the speed that I projected at is the initial projection velocity, which we're going to call u. At that moment, excuse me, at that moment, I push it both sideways and up. Are we okay with that? But I'm combining the motions together. So this, at the same time, even though I'm pushing it at an angle of u at the angle of theta, those are pushing it sideways as up at the same time. So how fast am I pushing it sideways? I'm pushing it sideways by this vector. That vector is the base of a right-angled triangle formed by u as its hypotenuse. The initial upward push would be given by that vector just there, uy. Now, trigonometrically, the horizontal vector, this one along here, is given by u cos theta. Now, the way I remember that is that's the symbol for u is, we use u for the initial projection velocity. So ux would be the initial horizontal velocity. And I use the way it's cos is close to the angle. So u close to the angle of theta. Okay? The initial vertical push, projection upward, is u sine theta. And I haven't got a mnemonic for that. I know it's just not close because it's not got cos in it. Okay? While we're here, if I wanted to get the furthest out of my board, my projectile, then I would make sure that theta is 45 degrees. So if angle is 45 degrees, then I will get the maximum range. Okay. If it's not, it'll go up too steeply and hit the ground too close, or if it's not 45, but it's a much shallower angle, it won't go up enough, it'll just go. Yeah. That's the technical term. Okay, so let's have a look at how to work out these two initial components. And we call them the initial components of velocity, ux and uy. Okay? There's one in your book that you can do in a few seconds. So here's an example. A projectile is launched at a velocity of 120 metres per second at an angle of 30 degrees to the horizontal. So this is a massive speed. 120 metres per second means that it can go from one end of the school to the other in 1 second in that side. So it's very, very fast. We're talking about a bullet here. Okay? And the gun is aimed at what angle to the horizontal? 30 degrees. So I'm aiming my gun at 30 degrees. It's probably best off if I say it's a rifle. Okay, at 30 degrees to the horizontal. And I pull the trigger, and the trigger, as it leaves the barrel, is 120 metres per second coming out of the barrel. Once it's left the barrel, no more forces act on it sideways. Once it leaves the barrel, the only force that starts acting on the bullet is the force of gravity, its weight, and it pulls it down. Rightio. So let's work out the horizontal velocity. It's u cos theta. So it's going to be u is 120, cos 30. Now cos of 30, people who remember, that is 0.866. And how many metres that is?
103.9.
103.9. We'll just go 104 metres per second. So this bullet is projected this way, as if we're pushing Jess 104 metres per second by the two horizontal ladies. Okay? Now, let's work out how much Jess is throwing her ball up in the air, her bullet in the air. So she'll be throwing up at 120 sine 30. Now we all know sine 30 should be, as an exact value, is a half, so it's 60. Okay? But most of the times when you're doing these things, it's not done for maths, it's done for physics, so therefore that could have been 35.2 degrees or whatever. So use your calculator. Are we okay with that? will you take a few moments to do question 5 in the book? Right, to fill, excuse me, to fill in the entire table, you need to be able to find the time of flight and the range and max height. Okay, so let's do it by this example here. We might want to take this one down. The equations that we're going to use are the ones from yesterday. These are your vertical equations of motion. Remember, the vertical motion is the one that changes. So it's got a lot of equations to describe those changes. The horizontal motion is boring. It simply is the same going sideways. It's just a constant sideways walk. Okay? So the only equation that you need to know, which doesn't appear on your HSC, is how to find the range. The range would be the sideways motion, the speed going sideways, by the length of time that it's moving sideways. The length of time that it's moving is called the time of flight, the TOF. Are we okay with what TOF is? Okay. So here is our example. A cannonball is projected 150 metres per second at 30 degrees to the horizontal. So here's our horizontal. Come on. There's our horizontal. And it's going to go up and down. Now, this is the simplest of all the projections. We call this projection shape ground to ground. Okay, are we okay why it's called ground to ground? And we're going to only look at ground to ground today. It's been projected at an angle of 30 degrees and 150 metres per second. To work with this, we use the UVART system again, with one addition. The UVART, we're going to put or have two U's at times. UX is the horizontal motion. All the other parts of the UVART are the vertical motions. Are we okay with that? So you don't always have to do this one, but you need UX for what thing that you're going to find. Range. So if you're not asked to find a range, you don't need UX at all. That's totally, is that making sense? The range is the only thing you'll be finding. We will be finding the range in a few more moments, so I'm not going to worry about it so much yet. Now, to find UY, how would I find that? Right, we use the triangle, which is the vector triangle. So, putting our little triangle together, what is our U? Our U is 150, and the angle is 30. So what is the vertical, what is UY? UY equals U sine 30, which is 150 sine 30, which equals 70, 75. Okay? Now, while we're here, we are going to work out UX, so I'm going to unrub that out. And UX would equal U cos 30, which is equal to 150 cos 30. Sorry, my 150 is gone, I think. So 0.9 of 150 is approximately 129.9. We will just go to 130 metres per second there to make this. Okay. Now, these are upward projections. So is UY a positive number? Yes. Where is the origin? The origin of the projection is here. Are we okay with that? Numbers above this are positive. Numbers below this are negative. Okay. Rightio. Now we've got that. we now can find the time of flight. To find the time of flight, at the top of the flight, Vy equals 0. Do you remember doing this yesterday? Now, because it's a ground-to-ground projection, if I find the time to the top of the flight, the time up to here, what will I do to do the whole flight? Just double it, wouldn't I? So we're going to find the time to get to the top, and because it's ground to ground, I will just say the time of flight is double that. Because what goes up must come down in the same way, without air resistance. Remember, all we are now doing with all of these equations here is pretending the ball is not going sideways. It's just going up and down. Are you clear on that? We know it's going sideways, but we're looking only at the time that will tail up and the time that it comes back down. So now we can do this. We're going to find at the top of flight it's 0. We know what the gravitational field is. It's negative 9.8. The time is what we're finding, and we don't know that. So I want to find the time when all these conditions are met. What formula would I use? Right, it's Vy equals Uy plus Ayt. Oops. And there's y's on all of those. Okay. So 0 equals Uy is 75 plus negative 9.8 times t. Solving that, bringing the negative 9.8 t over the side, dividing it into 75 gives us time as 7.7. Right, that's the time taken to go from the ground up to the top of its flight. What do I do this number to find the time of flight? Right, therefore time of flight is equal to 2 lots of 7.7, which is 15.4, is that right? 15.3 if you do the originals, okay? Seconds. Are we okay with that? All we are doing is we are ignoring the fact that it's also going sideways. We are just treating it as vertical motion under gravity. Right. To find the range. What do I need for the range? Right, range is equal to ux times the time of flight. Right, have we already found ux? Yes, it's 130. Have we found the time of flight? 15.3, and that means we've got a range of
1989.
1989 metres. So what have we just found? Oops. We've discovered how far it's moved sideways when it strikes the ground. Okay. The only thing else that I need to be able to work with this data for ground to ground is what is the maximum height? What is Y max? Y max is that distance there. There's Y max. Okay? And how would I do that? Well, at the top of the flight, what is 0? That. And this time we are finding distance, aren't we? We're finding that one. So let's redo that. Just clear all this stuff off. Let's give me a few seconds to get rid of all things. So what do we know? We are finding maximum height, which is on the next slide. So I'm not going to change it. So what do I know Uy is? Could you just tell me again? 75. Do I need Ux? No, what's Ux only used for? Find the range. Good. Vy, at the top of the flight, what is my vertical velocity? 0. Minus 9.8. Time is irrelevant, but we want to find the distance that this occurs. Distance when these are met. Now, we already know from doing our stuff overnight that this equation is right. It's the v squared one. V squared equals u squared plus 2ar with little y's on each of these. Okay. So shoving the values in, we get 0 equals 75 squared plus 2 times negative 9.8 ry. Solving for ry, that's 75 squared goes on that, becomes a negative, divides by 2 times negative 9.8. And we get ry being 287 metres. So we now know, oops, we now know that our projection being ground to ground, we know the range here is what we found. We know the height, that's y max. We know that was what it was projected at, and it's got two velocities at originally u, y, and ux. And they're the major features of a ground-to-ground projection. Okay? Right, in the next 5 minutes, and for your homework, now your homework will be completing the blue book up to and including question 5. So ensure that you go and use the textbook on that. Could you now complete question 1 on the sheet 2B, please? On worksheet 2B.